Dear students, now today we are going to solve question number 6. Question number 6 from Haloalkyl and Haloarine chapter. Okay, so can you see the question number 6 on the screen? So I can highlight it for you. Convert the following. Okay, question number 6, convert the following. Now we are going to convert propene to propanol first. So the first question is propene to propanol. Now let's see how to solve this. So propene, I'm writing here. So propene to propanol. Let's write in word first. Propene to propanol. Okay, propene means 3 carbon atoms. So we have to write double bond between 2 carbons. So CH2, CH3 and CH. Okay, so this is the structure of propene. And now propanol means again 3 carbon atoms, right? And CH3, CH2, CH2 and OH. One thing, they have mentioned 1 propanol. Propene to 1 propanol. So we have to convert CH3CH double bond CH2 to CH3CH2 CH2 OH. Now let's see how can we convert it. So CH3CH double bond CH2 plus we can add HBr to it. Now HBr we are going to add anti-Markovnikovly. So we have to do this reaction in presence of H2O2. So the HBr addition will take place according to anti-Markovnikov's rule. So AMR is anti-Markovnikov's rule. I am writing short form here. So see, why anti-Markovnikov's rule I have chosen is whenever any functional group is getting added to one position. Okay, so this is first carbon, second carbon and a third carbon. So if any functional group is getting added to first carbon, it means the functional group should be at first position. Okay, so if I add HBr without H2O2, I can do that addition here for you. HBr without H2O2, now here Markovnikov's rule will get applied. Now, according to Markovnikov's rule, negative part of the reagent get added to carbon which contain less number of hydrogen. So between these two carbon carrying carbon-carbon double bond, this carbon is carrying less number of hydrogen. So Br will get added to this carbon. So let's write CHBr and hydrogen will get added to this carbon. Now see, we are getting 2 bromopropane. Okay, and if we do further reaction of alkylation or reaction with aqueous alkali, then this Br will simply get replaced by OH and we will end up with the 2 bromopropane. I can write it for you. If we react it with aqueous NaOH or KOH or Ag2O, any, okay, heating, then we get CH3, CH, OH and CH3. So we will end up with the 2 propanol, but we have to prepare 1 propanol. Okay, so we have to do this addition CH3 CH double bond CH2 plus HBr in presence of H2O2, so that the addition will take place according to anti-Markovnikov's rule. So now I'm going to add this. So here product is CH3. Now this hydrogen will get added to this carbon. So CH3, CH2, CH2 and Br. So the product is 1 bromopropane. Okay, and this on further when we react with aqueous NaOH, KOH or Ag2O, any, then we get CH3, CH2, CH2 and OH. So now we have got the product 1 propanol. So we have to understand the difference. If we add HBr to propene. See, propene is unsymmetrical alkene. We are adding unsymmetrical reagent to unsymmetrical alkene. So addition will be according to Markovnikov's rule. Then we will get 2 bromopropane, and then on aqueous alkali hydrolysis, we get 2 propanol. But this is not the desired product. So what we have done, we have unsymmetrical alkene, we have unsymmetrical reagent HBr, and we are going to do this addition in presence of H2O2. This is most important, so that the addition of HBr will take place according to anti-Markovnikov's rule. So we will end up with the 1 bromopropane, and which on treatment with aqueous NaOH we will get 1 propanol as a product. So one more thing you can remember, H2O2 and HBr is the only combination where we can apply anti-Markovnikov's rule. CHF, HCl and HI, they do not react along with H2O2. So only HBr is the reagent which can react with H2O2, and we can do the addition as per anti-Markovnikov's rule. So this was about the first problem. Now let's go to second one. Now the next question is benzyl alcohol to benzyl cyanide. Now let's convert benzyl alcohol to benzyl cyanide. So let's write in word first, benzyl alcohol to benzyl cyanide. Okay, so benzyl alcohol, let's draw the structure first. So most of the students make this mistake. They just write OH over here and they call it as a benzyl alcohol, but this is not benzyl alcohol. Benzyl alcohol means benzene ring, then there is 1 carbon and then OH is attached to it. Okay, so always remember, whenever OH is directly attached to benzene ring, it is phenol, and benzyl means benzene ring plus 1, then 1 carbon and then the functional group. So if I ask you to draw structure of benzyl chloride, then always remember, benzyl chloride means benzene ring, then CH2 and then Cl, benzyl chloride. Okay, then benzyl alcohol. Now benzyl alcohol when treated with, okay, you can use any reagent. Suppose I am using a PCl3. Okay, so OH will get converted to Cl. Now why I am doing this conversion? Because see, we know we can convert any function alkyl halide to many functional group, like alcohol, then alkene, then cyanide, then isocyanide, then nitro, then nitrite, then primary amines, then esters. So we can convert alkyl halide to almost all functional group, right? So we have given starting material alcohol, and we know the method to convert alcohol into alkyl halide. So let's get this compound first into alkyl halide form, and then let's see how to convert further into benzyl cyanide. So now benzyl alcohol we have drawn, then PCl5 or PCl3, any reagent you can use. You need not have to balance reaction when it is a conversion, but still if you want to balance it, when it is PCl3, you take this starting material 3 times, then you will end up with CH2Cl, and this will be 3 times. Okay, and H3PO3 will be the end byproduct. Now we have got this benzyl chloride first. Now when we have benzyl chloride, what we have to do, we have to convert this chlorine into just CN. We have to change this Cl to CN. Now alkyl halide can be converted to cyanide. Now what is the method of doing this? It is when we treat it with alcoholic KCN. Okay, alcoholic KCN, then Cl get converted to CN, and now this compound is called as benzyl cyanide. So always remember, whatever the functional group, in the starting you have, just don't worry, just see how you can get it into halogen form. Once you have get the compound in halogen, we will have various, or we have various methods to convert this chloride into various functional group, or the halides into various functional groups. Now let's see what is the third problem. Now third is ethanol to propane nitrile. Okay, now again ethanol, let's write it down first in words. Ethanol to propane nitrile, right? Ethanol to propane nitrile. Now ethanol is what? CH3 CH2OH. Now there is no method, direct method to convert direct OH group into nitrile group. Nitrile is also a cyanide, always remember. So nitrile are also called as cyanide. So we have alcohol. Now we know alcohol can be converted to alkyl halide, and we know the method. We have used PCl3 in the previous problem. Now we can use SOCl2 here, right? So we will get CH3 CH2Cl, right? Then SO2 plus HCl. Okay, now SO2 and HCl are gases, so you get CH3 CH2Cl as a main product. Now when you convert this ethyl chloride, or when you treat this ethyl chloride with KCN, okay, which KCN? Alcoholic KCN, then Cl get replaced by Cn. This is nucleophilic substitution reaction. CH3 CH2 C triple bond N. Now you have got a product, propane nitrile. See, we can call this compound as ethyl cyanide. So there are two carbons, so ethyl and cyanide, or you can count all the carbons. So 3 carbons are there, so you can write this name as propane nitrile. Propane nitrile. So this is how we can solve this problem. Now let's see what is the next problem. Now the next conversion is fourth one, but1-in to N-butyl iodide. Okay, but1-in to N-butyl iodide. Let's write it down. But1-in to N-butyl iodide. Now see, 1-butene to N-butyl iodide. N-butyl iodide represents iodine is attached to first position. Okay, so long chain, and it is first iodine is attached to first carbon. So let's draw the structure first. CH3 CH2 C H double bond CH2. Now this is 1-butene or but1-in. You can write it in any way, 1-butene or but1-in. Now we have to convert it into N-butyl iodide, means CH3 CH2 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 and then I. See, they have not written 2-iodobutane. They have specifically written N-butyl iodide. N-butyl iodide, what is the IUPAC name? 1-iodobutane. Okay, this is 1-iodobutane. Now we have to do this conversion. How we can do that? Now 1-butene CH3 CH2 CH double bond CH2. Now in the previous problem we have seen, if we want any functional group at the first position, then we can use, or we can take help of HBr in presence of H2O2. So we can apply anti-Markovnikov's rule, and this Br will get attached to the carbon which contain more number of hydrogen atom as per anti-Markovnikov's rule. So CH3 CH2 then CH2, because we are going to add this hydrogen to this carbon and this bromine to this carbon. So CH2 and Br. Okay, so we have done this addition. Now we have bromine at the first position. What is the name of this compound? This is 1-bromobutane. Okay, now we have to convert bromine to iodine, and we know how to convert it. We have one name reaction, that is Finkelstein reaction, where we can convert chlorides and bromides into iodides, right? So what is the reagent for that? The reagent for that is NaI, and we use solvent as acetone. So bromine simply get replaced by iodine, so we get CH3, CH2, CH2, CH2 and I. So we have got 1 iodobutane, means N-butyl iodide simply. Okay, so this is how we can solve this problem. Now we can go to the next problem. Now next problem is 2-chloropropane, 2-propane, 1-ol. Okay, 2-chloropropane, 2-propane, 1-ol. Now look at the positions. Okay, 2-chloropropane, 2-chloropropane, 2-propane, 1-ol, propane, 1-ol. Okay, 2-chloropropane. Now let's see the positions first. The functional group in the starting material is at the second position, and functional group in the product is at the first position. It means, or it represents, we may have to go through alkene and then halogen addition like HBr in H2O2, and then we can convert the halogen into OH. So let's see, first let's draw the structure of 2-chloropropane. So CH3, CHCl and CH3. Okay, plus now we are going to use, what we are going to use here, alcoholic KOH. Now why I have chosen alcoholic KOH? Because see, we cannot directly convert Cl to OH from this position, because if I add aqueous KOH, or if I add aqueous NaOH or Ag2O, we simply end up with 2-propanol, and we don't want 2-propanol, we want 1-propanol. So what we can do is, we can remove this hydrogen first, and then let's see what happens next. So alcoholic KOH, what is the role of alcoholic KOH? Alcoholic KOH is a reagent which can do dehydrohalogenation. So halogen is attached to this carbon, means this is alpha carbon. Functional group is attached to this carbon, so this is alpha carbon, and the next two are beta carbons. Now we have beta beta because these two carbons are similar carbons. Okay, both are CH3 CH3s. So we can remove halogen from alpha carbon and hydrogen from any beta carbon. So let's do this. CH3. Now I'm not going to write halogen over here to alpha carbon, and I'm going to remove the hydrogen from this right hand side beta carbon. So now I have to write double bond between two, because we have removed one hydrogen and halogen. So we have got this alkene. Now we want something at the first position. Again, look at this first position. Now we know the method, we have already done it in the previous problem. Let's add HBr in presence of H2O2. We will add do the addition as per anti-Markovnikov's rule, then CH3, CH2, CH2 and Br, and then we can treat it with aqueous KOH or NaOH to form CH3, CH2, CH2 and OH. So now we have got 1-propanol or propane 1-ol. Just look at the structure, draw the structure first, then you just have to apply simple tricks. If the functional group is at the same position, then you can just simply add reagent and do the conversion. But if the functional group position is changing, then you may have to do removal first and then add again. So this strategy you have to use for each problem, and when you solve more and more problems, you will come to know how to do this conversion. So now let's move to the next problem. Now next problem is tertiary butyl bromide to isobutyl bromide. Okay, tertiary butyl bromide, let's write it down. tertiary butyl bromide to isobutyl bromide. Okay, so let's draw the structure first. Tertiary butyl bromide. Tertiary butyl bromide means CH3, CH3, CH3 and Br. So this is tertiary group. Why tertiary? Because halogen is attached to carbon, which is attached to 3 carbon atoms, and there is a but means 4 carbon atoms. So you have to arrange the structure like 4 carbon should be there and it should be tertiary. So I have written it like this. So we have to convert this tertiary butyl bromide to isobutyl bromide. Okay, isobutyl bromide. Let's see. Isobutyl bromide is what? CH3, CH, CH3 and then CH2, Br. So this is the structure of isobutyl bromide. You know this is the iso. Now we have to add one more carbon atom because it is butyl. So isobutyl bromide. Okay, then let's see how we can do this. So we may have to do elimination first in this problem as well, because if you see the arrangement of carbon, so arrangement of carbon is tertiary here and it is primary here. So let's see if we can solve this problem by doing elimination first. So suppose this is alpha carbon because halogen is attached to this carbon, and there are 3 beta carbon, but all the beta carbons are similar because they all are CH3, CH3, CH3. So let's write it down again. CH3, CH3, then again CH3 and then Br. Now add alcoholic KOH. Alcoholic KOH is always used to do dehydrohalogenation. So we are going to remove halogen from alpha carbon and hydrogen from any beta carbon. So if we remove this hydrogen from this beta carbon, then let's see, suppose I am removing hydrogen from this carbon. Okay, then this will become CH2. Now I am going to remove halogen from this carbon, then we have to put double bond between these 2 carbon because we have removed something from there. Now this is our product. Now there we have, what we have to do, we have to add bromine again and hydrogen again. So we can do addition of HBr and H2O2 again in this reaction because this bromine is attached to first position, and we know when we want any functional group at the first position, then we can proceed through HBr and H2O2 addition to alkene. So you just remember this. Now I am adding Br to this carbon and this CH, now CH3 and a CH3. I am writing this CH3 here, just that's it. Okay, and now see what we have got. We have got isobutyl bromide. So this was also simple problem. We may feel it is difficult because the carbon arrangement is different, but you just try and solve it. There is no rocket science. You can easily solve these problems. Now let's move to the next problem. Next problem is para nitrochlorobenzene to para nitrophenol. Okay, para nitrochlorobenzene to para nitrophenol. So let's draw the structure first. Para nitrochlorobenzene. So I have written nitro to the para from chlorine, and we have to convert this into phenol, means OH is changing to Cl is changing to OH. Now we know if there is no NO2 written and if there is only chlorobenzene and we have to convert it into phenol, then this reaction is really difficult to proceed because haloarenes, they do not undergo nucleophilic substitution reaction. We know that. But there is an electron withdrawing group present at the para position, and that's why this reaction is possible. So you just have to write simple reagent, that is aqueous NaOH, okay, and heat. So after heating, the Cl will get converted to OH. But see, just one point you remember, if you have only chlorobenzene and if you want to convert it into phenol, then you can use reagent NaOH, but you have to apply more than 600 degree 600 to 650 degree Celsius temperature, and we need to apply pressure as well. Okay, so only then this reaction is possible, but product yield is also not very good. So because this nucleophilic substitution is not possible in case of aryl halide, but we can do this nucleophilic substitution whenever there is electron withdrawing group like NO2 are present on ortho and para position or on either of the position. So this was the one. And now last is propane to 1 nitropropane. Okay, propane to 1 nitropropane. Let's solve this one as well. First write it down. Propene to 1 nitropropane. Propane to 1 nitropropane. Now CH3 CH double bond CH2. This is propene, and we have to convert it into CH3 CH2 CH2 NO2. Okay, so we know functional group is again on the first position. So now you will also be able to tell me what is the reagent. This is HBr in H2O2, anti-Markovnikov's rule. Then bromine will get added to first carbon, and now we have 1 bromopropane. And when you treat this 1 bromopropane with silver nitrite solution NO2, then we get CH3 HEO and NO. Okay, then we get CH3 CH2 CH2 and NO2. So this is how we can prepare 1 nitropropane from propane. Just simple addition of HBr in presence of H2O2 and then treat it with silver nitride. We will end up with 1 nitropropane. So this was about the conversion. We will see the next questions in the next video. Thank you.